Hi, this is Haomeng presenting our CVPR 2023 work, Hyperspherical Embedding for Point Cloud Completion. This is a joint work with Jimmy and Bram from University of Michigan and Matthew from Carnegie Mellon University. We observed that traditional encoder and decoder architecture for point cloud completion learns sparse embedding distribution, which leads to worse generalization results during testing. Also, in the multitask learning setting, existing architectures tend to have worse performance compared to learning each task individually due to different embedding distributions and optimization conflicts. To solve these problems, we propose a hyperspherical module which could be inserted into any existing encoder and decoder architecture for point cloud completion. By theoretically analyzing the effects and empirically conducting experiments on state-of-the-art baselines and datasets, we show that our proposed module could consistently improve the point cloud completion result in both single-task and multitask learning. Now, we provide more details of our method. Our hyperspherical module consists of an MLP layer and a normalization layer. We take the L2 norm of the embedding after the transformation from the MLP layer. We insert this module after the original embedding in the baseline models and use the hyperspherical embedding after the module for downstream tasks. On the right, we show the equation for the hyperspherical embedding, where F is the embedding after the MLP transformation, and F hat denotes the normalized embedding. Now, I will theoretically introduce some effects of applying the hyperspherical embedding. The first proposition is that the gradient of the embedding before normalization is orthogonal to itself. Here's the gradient to the embedding using chain rules, where we have F hat as the normalized embedding. The orthogonality proof is shown here. We could find the dot product between the original embedding and the gradient is always 0. On the right, we show the relationship between F and its gradient, where the embedding F is shown in black and the gradient is shown in blue. The second proposition is that for standard stochastic gradient descent, the magnitude of the embedding before normalization increases at each update during training. Empirically, we find this also holds for other popular SGD-based optimizers. This is the figure from last slide. From proposition 1, we know the gradient, shown in blue, is always proportional to the embedding F, which is shown in black. So, the total update, shown in orange, would always be greater than the original embedding F in last step. We further show the figure of L2 norm of the embeddings with different architectures on MVP test set. The blue one on the left shows the embedding norm histogram without any constraints. The green one in the middle shows the norm only with the MLP layer, and the orange one on the right shows the norm with the whole module. We could see with the normalization layer, the embedding norm would get much larger. The third proposition is that the magnitude of the gradient is inversely proportional to the norm of the embedding. This could easily be derived from the equation of the gradient to the embedding. The norm of embedding trained with a larger learning rate quickly increases until an appropriate effective learning rate is reached. When using unconstrained embeddings, the model may overshoot the minima during training and might not get converged. Here is a figure showing the performance of multitask learning for different baseline models on MVP dataset. The blue solid line shows the completion with unconstrained embeddings, and the orange solid line shows the result with our module. We could see that under certain learning rate, the training could easily get diverged for those baselines, while with our module, we could consistently achieve good completion results under a wider range of learning rates. The last proposition is that the increased norm of F requires a poorly conditioned weight matrix. If we decompose the weight matrix using singular value decomposition, the norm of the transformed output F is only related to the singular values in the diagonal matrix sigma. From proposition 2, we know the norm of F is increasing, so the weight W will be updated with greater singular values. If all singular values get increased, then the scale of the weights would increase, and larger weights will lead to overfitting. Empirically, we did not observe this effect. In fact, large singular values become larger, and small singular values become smaller, while the scale of the weight matrix is still similar. This leads to a more poorly conditioned weight matrix. Here's a figure showing the distribution of singular values for different baseline models on MVP dataset. We could see that with the hyperspherical embedding shown in orange, the largest singular value will increase, and most of other singular values would get decreased. The poorly conditioned weight matrix will reduce the complexity in the high-dimensional input and lead to a more compact distribution. Here we show the distributions of cosine similarity on MVP dataset. We could see with our proposed module showing in orange, the cosine similarity for all classes and inside specific class would be much higher. This compact embedding distribution helps the model generalize well on unseen data at testing. We also show the gradient conflicts between tasks in multitask learning during training. We could see with the proposed module, the gradient cosine similarity would be larger during training, which indicates smaller gradient conflicts. Now, I will show more experiments and visualizations of our method. Here is the quantitative results for point cloud completion on MVP dataset. The numbers shown in the table are the chamfer distance multiplied by 10 to the power of 4. We could see that we could achieve consistent improvement for all baseline models with our hyperspherical module. Here is the qualitative results for point cloud completion on MVP dataset. From the figure, we could see that with our hyperspherical module, the completion result has less noise. Here is the quantitative results for multitask learning on MVP dataset. The second large column shows the result for single-task learning on classification and completion. The later columns show the result of different multitask learning settings and techniques on these two tasks. From the figure, we could see that we could achieve consistent improvement on completion task over all multitask learning methods without hurting the performance of classification task. From the last column in the table, which compares the completion result in single-task learning and multitask learning, we could see our method could achieve better completion result in multitask learning than in single-task setting. We further show our method on some real-world datasets. Here we show the result for object detection, pose estimation, and point cloud completion on GraspNet dataset. The proposed hyperspherical module brings consistent improvement over all these tasks, which further proves the robustness of our module. In this figure, we show some samples of point cloud interpolation in the embedding space. We could find the generated point clouds with hyperspherical embeddings have more clear clues from source to target shapes, which proves that with our module, we could have a more compact embedding space. To conclude our work, we propose a hyperspherical module that outputs hyperspherical embeddings, which improves the performance of point cloud completion. We theoretically investigate the effects of hyperspherical embeddings and demonstrate that the point cloud completion benefits from them by stable training and learning a compact embedding distribution. We analyze training point cloud completion with other tasks and observe conflicts between them, which can be reconciled by the hyperspherical embedding. If you are interested, please refer to our paper for more details. Thanks for watching.